Did gamma rays cause Earth's deadliest extinctions? Imagine a dying star whose final breath could outshine the entire history of your existence. NASA scientists tracked these cosmic time bombs, called gamma ray bursts, that release more energy in seconds than our sun generates in billions of years. In October 2022, astronomers witnessed the brightest gamma ray burst ever recorded, nicknamed the BOET, brightest of all time. Had that burst occurred in our galactic neighborhood and been pointed at Earth, our civilization might have been erased from history. So how close have we come to cosmic extinction, and could ancient GRBs, reshaping the very path of evolution, explain Earth's deadliest mass extinctions? The Ordovician extinction, Earth's first cosmic catastrophe? What if the first major mass extinction on Earth wasn't caused by volcanic activity or an asteroid, but by radiation from space? About 445 million years ago, our planet experienced the Ordovician-Silurian extinction event, the first of the big 5 mass extinctions that have punctuated Earth's history. This catastrophic event eliminated approximately 85% of marine species, fundamentally altering the course of life on our planet. The Ordovician period was a time when a majority of life existed in the oceans. There were no plants or animals on land yet, just a vast expanse of barren rock. Beneath the waves, however, life flourished in remarkable diversity. Trilobites scuttled across the seafloor alongside primitive fish, while corals, mollusks, and countless invertebrate populated the ancient seas in a thriving underwater ecosystem that seemed stable until something triggered a devastating collapse. Imagine a sudden, global catastrophe striking this vibrant marine world, like a cosmic switch being flipped, extinguishing life across the planet. What makes the Ordovician extinction particularly intriguing is its unusual pattern. The extinction unfolded in 2 distinct pulses separated by approximately 1 million years, a cosmic heartbeat that would forever alter Earth's evolutionary trajectory. During the first pulse, many species vanished rapidly across widely separated geographic regions, from what is now North America to areas that would become Europe and China. This simultaneous global impact is difficult to explain through localized phenomena. The traditional explanation for this extinction has centered on climate change triggered by continental movements. According to this theory, the ancient supercontinent Gondwana drifted over the South Pole, triggering massive glaciation that locked up ocean water in ice caps. This supposedly caused sea levels to drop dramatically, destroying shallow marine habitats where most species lived. But a closer examination reveals problems with this explanation. The fossil record shows that species disappeared too rapidly and too uniformly across different latitudes for a gradual climate shift to be the sole culprit. While climate change certainly played a role in the extinction, the trigger for this climate shift has remained mysterious. In 2004, a team of researchers from the University of Kansas proposed an alternative hypothesis that could explain these anomalies. Perhaps a gamma ray burst, GRB, from a nearby stellar explosion triggered the Ordovician extinction. This hypothesis was based on careful analysis of the fossil record and the unique signature a GRB would leave behind. Dr. Adrian Malott and his colleagues noted several features of the Ordovician extinction that aligned with their GRB hypothesis. First, the initial extinction pulse shows a pattern of rapid, simultaneous species loss across vast geographic distances, exactly what you'd expect from a global radiation event. Second, the fossil record reveals evidence consistent with radiation damage rather than just environmental change. The researchers identified fossilized malformed plant spores from the Ordovician period that show patterns of damage similar to what we see in modern plants exposed to UV radiation. While this evidence comes from later periods than the Ordovician, it establishes a precedent for identifying radiation effects in the fossil record. These malformations appear suddenly in the geological record, suggesting a rapid onset rather than gradual environmental deterioration. The double pulse pattern of the Ordovician extinction aligns with GRB impact models. The initial burst of gamma radiation would strike Earth in a flash, lasting from a few seconds to minutes, triggering the first extinction pulse through direct radiation effects and atmospheric changes. The second pulse would follow as the damaged ozone layer allowed harmful UV radiation to reach the surface, creating ongoing ecological stress that eliminated species that initially survived. To test scientific plausibility, researchers calculated the probability of Earth being struck by a gamma ray burst during its history, using data on GRB frequency observed throughout the universe, typical energy outputs, and Earth's position in the Milky Way galaxy over time. Scientists performed complex statistical analyses. Their calculations yielded a surprising result. There's approximately a 50% chance that Earth has been hit by at least one lethal gamma ray burst in the past 500 million years. Among the 5 major mass extinctions, the Ordovician event shows the strongest correlation with the expected effects of a GRB impact. If a gamma ray burst did trigger the Ordovician extinction, it would have unfolded something like this. A distant star, perhaps thousands of light years away, reached the end of its life in a spectacular supernova explosion. For a brief few seconds, this dying star focused an intense beam of gamma radiation into space. By cosmic chance, Earth happened to lie in the path of this beam. When the gamma rays reached our planet, they would have created a light show in the night sky brighter than a full moon, but most of their energy would have been invisible. The real damage would have occurred in the upper atmosphere, where the gamma rays would have triggered a cascade of chemical reactions, converting nitrogen and oxygen into nitrogen dioxide, effectively creating a brown haze of smog worldwide. This atmospheric transformation would have blocked some sunlight, causing rapid global cooling. More importantly, the nitrogen oxides would have catalytically destroyed the ozone layer, allowing harmful ultraviolet radiation from the sun to penetrate to Earth's surface and into the shallow oceans where most marine life lived. Marine organisms that had evolved in an environment protected from UV radiation would have found themselves suddenly exposed to damaging levels of ultraviolet light. DNA damage, reproductive failure, and ecosystem collapse would have followed. What makes the GRB hypothesis compelling is how it unites disparate evidence. It explains the rapid, global nature of the extinction, accounts for the double pulse pattern, and helps explain why organisms in shallow waters suffered most severely. As Thomas Johnson, a paleobiologist not involved in the original research, noted, the GRB hypothesis provides an elegant solution to several long-standing puzzles about the Ordovician extinction. His assessment highlights why many scientists now consider this cosmic explanation a serious possibility, even if absolute certainty about this ancient catastrophe remains elusive. Cosmic time bombs, the science of gamma ray bursts. Considering cosmic influences means confronting an unsettling reality. The universe regularly produces explosions that dwarf our most destructive weapons by factors beyond comprehension. These gamma ray bursts release more energy in mere seconds than our sun will produce in its entire 10 billion year lifetime. And until recently, scientists couldn't explain what natural mechanism could possibly generate such devastating power. When astronomers first detected these mysterious bursts in the 1960s, they faced a profound puzzle. What cosmic process could possibly generate such immense energy? The journey from mysterious signals to understanding these cosmic flashbulbs took decades, revealing some of the most violent events in our universe. Today, scientists classify gamma ray bursts into 2 distinct categories that unveil fundamentally different cosmic processes. Long bursts, lasting more than 2 seconds, emerge from the catastrophic deaths of massive stars. Short bursts, lasting less than 2 seconds, result from the collision of some of the densest objects in the universe. Long gamma ray bursts occur when stars at least 10 times more massive than our sun reach the end of their lives. Unlike smaller stars that might quietly fade away, these stellar giants create cosmic spectacles of extraordinary magnitude. The process begins deep inside a dying massive star. After exhausting its nuclear fuel, the star's core collapses catastrophically under its own gravity, creating a black hole in mere seconds. As this newly formed black hole devours the infalling stellar material, it forms an accretion disk. Imagine a whirlpool of superheated gas spiraling inward at tremendous speeds. This chaotic environment generates two opposing jets of particles accelerated to nearly the speed of light, blasting outward from the rotation poles like cosmic searchlights cutting through the darkness of space. Astronomers call this the collapsar model. Capturing how a stellar giant's collapse creates these extraordinary energy beams. Short bursts present an entirely different cosmic scenario. They typically result from the collision of two neutron stars, incredibly dense remnants containing the mass of our sun, compressed into a sphere roughly the size of a city. A single teaspoon of neutron star material would weigh billions of tons on Earth. When these extraordinary objects spiral into each other, they create a black hole through a process distinct from the collapsar model. The impact of these super-dense objects generates perfect conditions for cosmic alchemy, the formation of some of the heaviest elements in the universe. During these collisions, atomic nuclei rapidly accumulate neutrons to form gold, silver, platinum, and other precious metals that eventually find their way into planets like Earth. Every piece of gold jewelry you own likely originated in such a violent cosmic merger billions of years ago. In some cases, short bursts may also result from a neutron star merging with an existing black hole. The energy scale of these cosmic explosions challenges human comprehension. A typical burst releases more energy in a few seconds than our entire sun will emit during its 10 billion year existence. An output so massive that converting Earth's entire mass perfectly into energy would still fall short of the most powerful bursts observed. These bursts aren't omnidirectional, but produce focused beams that slice through the cosmos like celestial spotlights. This directionality explains why we detect only a fraction of all gamma-ray bursts. We only see those where the beam points toward Earth. The focused nature also explains their destructive potential. When a burst points directly at a planet, it concentrates its energy rather than dispersing it equally, potentially affecting worlds that lie in its path. Scientists estimate gamma-ray bursts occur approximately once per day across the observable universe, mostly in distant galaxies billions of light years away. Their tremendous brightness allows detection even at these extreme distances, making them valuable cosmic beacons for understanding the early universe. The detection of these events represents a triumph of modern astronomy. Gamma rays don't penetrate Earth's atmosphere, so their discovery awaited the space age when detectors could be placed above our protective shield. The first bursts were actually discovered accidentally by satellites monitoring nuclear test ban treaties in the 1960s. Scientists initially considered possibilities like alien civilizations or secret nuclear tests before discovering the truth. Gamma-ray bursts represent the most energetic electromagnetic events since the Big Bang itself. Supernovae, solar flares, even active galactic phases, none compare to the raw power of a gamma-ray burst at its peak. This enormous energy output creates an intriguing possibility. These bursts might be visible across much of the observable universe. Some scientists suggest advanced civilizations might harness artificial gamma-ray bursts as beacons to announce their presence across intergalactic distances. But for life-bearing planets, these cosmic lighthouses represent potential extinction events. Their energy can strip away protective atmospheric layers and bathe planetary surfaces in lethal radiation, especially if a burst occurs relatively nearby, with its beam pointing directly at an unfortunate world. Research continues to yield new insights. Recent observations have identified ultra-long bursts lasting hours instead of seconds, suggesting additional creation mechanisms we don't yet understand. Others have shown evidence of gravitational waves accompanying short bursts, confirming their origin in neutron star mergers and opening new avenues for multi-messenger astronomy. Atmospheric assault: how gamma rays attack Earth's shield. What stands between us and the harsh radiation of space? A fragile layer of ozone, just a few millimeters thick if compressed to sea level pressure. When a gamma ray burst strikes this delicate shield, it triggers a cascade of atmospheric chemistry that transforms our protection into vulnerability. Unlike many cosmic threats that directly impact Earth's surface, gamma ray bursts wage their assault through more subtle means. The gamma rays themselves don't penetrate to ground level. Instead, they unleash their destructive potential by fundamentally altering our atmosphere's protective chemistry. This invisible attack makes GRBs particularly insidious, as their most devastating effects unfold through a series of atmospheric chain reactions. The ozone layer, our thin atmospheric armor, absorbs the majority of the sun's harmful ultraviolet radiation before it can reach the surface. This slender shield of triatomic oxygen molecules protects all terrestrial life from DNA-damaging radiation. Without it, life as we know it couldn't exist on land. But this protective veil becomes surprisingly vulnerable when confronted with a gamma ray assault. When gamma rays penetrate our upper atmosphere, they immediately ionize atmospheric gases, splitting apart nitrogen and oxygen molecules. This splitting creates nitrogen oxides that act as catalysts, systematically dismantling our ozone shield molecule by molecule. Each nitrogen oxide can destroy thousands of ozone molecules before being removed from the atmosphere, a devastatingly efficient process. The scale of potential destruction is sobering. Models indicate that a mere 10-second exposure to a nearby gamma ray burst could deplete up to 75% of the ozone layer in regions directly exposed to the radiation. Global ozone levels could drop by as much as 38%, creating a worldwide crisis far exceeding any atmospheric damage humans have ever caused or witnessed. This depletion wouldn't manifest as a uniform thinning. Instead, it would create dangerous holes in our protective shield, similar in concept to the Antarctic ozone hole from chlorofluorocarbons, but potentially far more extensive. Through these atmospheric wounds, harmful ultraviolet radiation would flood onto Earth's surface at levels life hasn't experienced since before the ozone layer formed. The geographic distribution adds another layer of complexity. When gamma radiation enters the atmosphere over a polar region, the depletion becomes concentrated there rather than spreading uniformly. This occurs because the radiation produces chemical changes primarily in the middle atmosphere, and atmospheric transport flows predominantly toward the pole. Consequently, polar regions could experience even more extreme ozone destruction than global averages suggest. Our atmosphere wouldn't remain compromised permanently. Models suggest the ozone layer would gradually recover over approximately 5 to 7 years. During this recovery, ozone in the lower atmosphere might measure around just 10 parts per billion, varying seasonally. Imagine stepping outside into a sun that burns without mercy day after day for years. A world where shadows become sanctuaries and exposed skin blisters within minutes. The severity depends largely on the fluence of the burst, essentially the total energy delivered per unit area. A more energetic burst, or one directed more precisely at Earth, would cause greater atmospheric disruption. Local ozone depletion in the worst affected regions could reach 74%, creating areas where almost no protection remains against the sun's ultraviolet radiation. Visualize our atmosphere as a complex chemical factory with carefully balanced production lines. Gamma rays sabotage key workstations, causing harmful compounds to form while shutting down protective processes. The factory doesn't explode, it begins manufacturing the very chemicals that slowly dismantle its protective systems. This atmospheric damage represents a fundamental difference from other extinction-level threats. An asteroid impact or supervolcano eruption would affect our atmosphere primarily through dust and debris that eventually settle. The chemical changes triggered by gamma ray burst would be more persistent, altering atmospheric chemistry for years after the burst has passed. The atmospheric ozone we rely on daily exists through a delicate balance of formation and destruction. Oxygen molecules split by ultraviolet radiation from the sun allow individual oxygen atoms to combine with other oxygen molecules to form ozone. The gamma ray burst shifts this equilibrium by introducing new destruction pathways that overwhelm the natural formation processes. Our modern understanding comes from sophisticated atmospheric models combining astrophysics with atmospheric chemistry. These reveal that even a relatively distant GRB could trigger significant ozone depletion if Earth happens to be in the path of its narrow beam of radiation. Perhaps most concerning is how quickly this transformation would occur. Unlike climate change or other gradual atmospheric alterations, the chemical reactions initiated by a gamma-ray burst would begin immediately and accelerate rapidly. Within days, significant ozone depletion would already be underway. Ecosystems would have little time to adapt as the sky itself becomes a threat. This atmospheric assault would ultimately transform Earth's surface environment through the flood of solar ultraviolet radiation penetrating the compromised ozone layer. UVB radiation, causing sunburns and DNA damage, would increase dramatically. The more energetic UVC radiation, normally completely blocked by our atmosphere, might reach the surface in measurable amounts for the first time in Earth's recent history, bathing the planet in radiation hostile to the very foundation of life. Extinction Cascade, life under deadly skies. As deadly UV radiation floods through the atmospheric wounds, a silent extinction would begin unfolding across Earth's surface. The organisms we rely on most would face the greatest peril. This isn't just about individual species struggling. It's about the collapse of the fundamental biological systems that maintain life as we know it. In the oceans, microscopic phytoplankton would become the first major casualties. These tiny organisms form the foundation of the entire marine food web and generate approximately half of our planet's oxygen supply through photosynthesis. Their cellular structures, evolved in an environment historically shielded from extreme UV exposure, possess minimal natural defenses against radiation. Diatoms and coccolithophores, two common phytoplankton types crucial for carbon cycling, would suffer severe DNA damage when bombarded by UVB and the normally blocked UVC radiation, disrupting their delicate molecular machinery. Within days, the damage would be evident across entire phytoplankton populations as their photosynthetic efficiency plummets. Research on Antarctic phytoplankton has demonstrated that even moderate increases in UV exposure can reduce their growth rates by 30%. And a post-gamma ray burst scenario would subject them to radiation levels far beyond anything in our recent planetary history. The effects would rapidly travel upward through the marine food chain. Zooplankton would starve as their food source disappears. Fish populations would subsequently crash, affecting species that rely directly on plankton, then extending to larger predatory fish. The entire marine ecosystem would begin unraveling from its foundation. On land, terrestrial plants would experience an immediate assault on their photosynthetic capabilities. The intense UV radiation would degrade chlorophyll molecules, essentially disabling plants' ability to convert sunlight into energy. Cellular damage would accumulate rapidly, with radiation directly attacking plant DNA. Particularly vulnerable would be staple crops like wheat and rice, whose shallow root systems and exposed growth patterns leave them with little natural protection. Plant reproduction would suffer dramatically. Pollen viability would decrease, and the delicate tissues of flowers and developing seeds would experience disproportionate damage. Within seasons, widespread plant communities would transform radically, with certain species vanishing entirely while others maintain reduced populations. Surface-dwelling animals would face devastating challenges. Unlike microorganisms with rapid reproduction cycles that can quickly adapt through natural selection, larger animals with longer generation times would have no opportunity for evolutionary adaptation. Their exposed tissues, particularly eyes and skin, would suffer immediate and cumulative damage. Animals would develop severe radiation burns, weakening their overall health and making them vulnerable to infections. Vision impairment and blindness would become widespread as sensitive ocular tissues absorb harmful radiation, hampering hunting, foraging, and predator avoidance. Immune systems would gradually collapse as UV radiation damages white blood cells. Amphibians, already experiencing global declines, would be particularly vulnerable as their permeable skin offers minimal protection against radiation. Natural adaptations would determine survival chances. Animals with pigmentation like melanin would gain some protection. Those with thick fur, feathers, scales, or shells would fare better than animals with exposed skin. Nocturnal species would have a significant advantage over diurnal ones, venturing out only when the sun's radiation is absent. Geographic position would play a crucial role in determining fate. The poles would likely experience the most severe ozone depletion, making polar ecosystems particularly vulnerable despite their limited sun exposure. Equatorial regions might retain more ozone protection, but would still experience dramatically increased UV exposure. 3 groups stand out as potential survivors. Deep-sea organisms would remain largely insulated from the catastrophe. Water effectively absorbs UV radiation, with significant attenuation occurring in just the first few meters. Creatures living hundreds or thousands of meters below the surface would continue their lives largely unaffected, protected by the water column above them. Burrowing animals that spend most time underground would find unexpected sanctuary. The soil would block virtually all harmful radiation, allowing these species to continue their subterranean lives while surface dwellers perish. This includes earthworms, burrowing insects, and mammals like moles and prairie dogs, which might emerge occasionally for food, but quickly retreat to safety. Extremophiles, organisms already adapted to extreme conditions, form a third group with superior survival potential. Many have evolved sophisticated DNA repair mechanisms that allow them to withstand normally lethal radiation levels.